So today is the start of week 7 in the course, and the topic of this week is the IV regression, or the instrumental variable regression. And this is basically chapter 12 of your textbook. And I'm reminding you that next week we have the midterm, and I'm going to go over that today also. And this is one thing that I want to edit, because I decided to make the exam covering week 1 to week 6 instead of week 1 to 7. We're moving kind with a bit of a lag, which I like. Since let's say today we're going to be covering the materials of last week with some application. So I said, okay, let me make the coverage of the midterm only up to week 6. Okay, so like this topic is not part of the midterm. For this topic, we have videos already posted for you, and these videos were actually created for another econometrics class, same materials, same everything. So I want you to watch video of the IV regression part 1, part 2, 3, and 4, and these are very, very, very helpful. Okay, so for this week you have 4 videos to watch and take notes, and next week, which is our midterm, the week after our midterm, we're going to practice the IV regression together, like with Stata applications. Okay. Our in-class practice today is 2 parts. So it's about the last week's topic, binary dependent variable. Okay, I have a Stata and a non-Stata practice question for you. For the Stata part, I have already sent you the data set, which is the charity DTA. I have also an Excel form of the data, which I sent by email. Sometimes for some computers, the DTA file doesn't like work with Sakai. We have the data description, and we have here the PDF file of the questions. All right. The non-Stata part is a question, again, about the binary dependent variable. It's a PDF file here. After we're done with answering the question, I will be posting for you the solutions, like the do here and the solution PDF here. Again, I keep reminding you guys that you always have an option to earn extra credits. Each practice is worth 3 points, okay? Some of these practices would count for your midterm, and others would count for your final exam. I don't have like any decision yet on which practice is related to the midterm or the final yet, but most likely the first 3 are related to the midterm and the next 3 are related to the final exam. Okay, I encourage you to do it. Currently, I have only 2 students who have submitted the first 2 practice of Stata. I highly encourage you guys to go over these practices, and I made your life easy. I'm just like walking you through most of these practices, and it shouldn't be like too challenging, especially if you watch like, or if you keep watching all my videos. Okay, if I ask you any question, whether this is in a practice, assignment, or homework, or quiz, or an exam, I always make sure that you have seen it before in a different way, in a different practice. Okay, so just make sure that you keep watching my videos. Okay. Just before I leave Sakai, I just want to go show you week 8 for the midterm. And as I said, it's next week, our midterm. I was able to edit this one, so it's from week 1 to 6 only. So midterm is not covering week 7. It consists of 2 parts, and this is similar to your homework 2 and 3. Homework 2 and 3, you have 1 part in my lab and another part in Sakai. Okay, so this is the same thing for the midterm. Okay. The first part, I have it here like written for you so that you're not confused. First part, You go to my lab, take it for 1 hour and a half. Second part, you come to Sakai and take it for 1 hour and a half. I don't have any preference, like which one you're gonna start first. It's up to you. As long as you take it within the 24 hours of Wednesday, the 21st. Okay, I'm not sure why I'm writing it as Wednesday, so let me change that. It's gonna be like during our class days, which is Mondays. Okay, so this is gonna open next Monday. Next Monday we're not gonna meet, so on Monday we're gonna have the midterm as if we're having it in class, but it's even easier because I'm going to give you like 24 hours. Anytime you open the exam within the 24 hours, you have 1.5 hours, an hour and a half on Sakai and an hour and a half on my lab. Okay, I have already for you here the data description, different formats. I'll make sure also to send these files by email just in case. All right, and you should be able to see the link here on Monday. Okay, so let me just take a note that I need to change this because I want to make it on the same day, which is the 19th, which is a Monday. All right. Okay. And then you will have the discussion for here posted for next week. Okay. Any question before we start? Okay, so what we're gonna do today is, as I said, we're moving with a lag. So we are, yes, in week 7, as I said. However, we're not covering this topic today. We're going to go over some parts in the binary dependent variable because I have already posted for you videos, right, for the binary dependent variable. What I'm going to do today is just I'm going to fill the gaps of some of the information that are not covered in the 3 videos. So I'm going to start with that. I'm going to start with the 3 different binary dependent variable models. And I'm going to show you 2 applications, one which is right from your textbook, second one which is a Stata question, third one which is a non-Stata question. So I hope after today's class, this topic would be like relatively less challenging because I know some students, they find it, you know, it's not easy to understand, especially that we're not used to a dependent variable that takes only 1 and 0. Okay, so let's start. Let me take you to my iPad. So okay, so this is not the slide I want to start with. Okay. Okay, so our topic is the binary dependent variable. Okay, so we used to have a model in which y equal beta naught plus beta 1 x, let's make it just a simple model, okay, plus ui, and we used to have y as a continuous variable that takes different values, okay, and xi is a continuous. This topic, however, is talking about the dependent variable. And this dependent variable is only taking 2 values. So yi can be 1 or 0, and that's it. Okay, so something happens or does not happen. So let's say family own a house, okay, or not. like you don't have anything in between. You pass or fail. What else? You graduate or not. You find a job or labor participation, yes or no job. Okay, so it's either or. Okay, we don't have any values in between. And in these types of binary dependent variable models, we have 3 different ways to estimate our model. And just note that this topic is talking about the dependent variable is being binary. We really don't care about the x. The x can be binary or not. Like we have already dealt with x as being 1 and 0, like male and female, graduate or 0, you do not graduate, right? Age above 39 or not, or below, okay? So we have dealt already with x being binary, but we haven't covered any topic or any model in which y is being binary. So that's why the focus of this topic is on the dependent variable. What about x? X can be binary or not. We really don't care about that, okay? So there are 3 ways to estimate these models, and I'm kind of repeating some information that you guys have already seen in my videos, which I'm intending to do that, okay? So we said we have 3 different models to estimate this regression when y is binary. We have the first one, which is a linear probability model. We have a probit model. We have logit model, okay? This is not recommended at all because it has some disadvantages, as we're gonna see. So currently, if you have y that is being 1 and 0, it is recommended that you either use probit or logit. And probably like 20 years ago, before the invention of computers and statistical softwares, people used to prefer the logit because it's easier to compute as compared to the probit. Okay, so this one you can use it by, you can compute it using the calculator because it's an exponential function, as we're gonna see. However, the probit model is not. Nowadays, because we have Stata and we have other different types of statistical softwares, actually people have zero preference on which one they prefer, because I can use Stata and get my results, right? And both are going to give me very, very, very close result. So let's start. So again, I said that I do not prefer to use the linear probability model because it has some disadvantages, but we have to go through it first. So the linear probability model, as the name suggests, it's linear, okay? So when I say that y takes an outcome that is 1 versus an outcome that is 0, I'm also interested in knowing what is the probability of being 1 and what is the probability of being 0. So I will need to attach certain probability for being 1, and I call it pi, and I need to attach some probability of being 0, which is the rest. Okay, so if I want to compute the estimated y or the expected y, my expectation for the y given xi, any expectation is an outcome times a probability, okay? And I do have both an outcome and I have probability. So this expectation is going to be equal to 1 times outcome times probability of taking 1 plus, right? 0 times the probability of being 1 minus pi. And of course, 0 times anything is gone. So this expectation is pi. In other words, the expectation of yi given xi is simply the probability that y appears to be equal to 1 in my data set. So this actually makes our life easy, okay? In other words, the yi hat is equal to this expectation of, let me keep it like same notation because I don't want to keep changing. Let me just use, so yi hat is the expectation of yi hat given xi, which is simply equal to the probability pi. And since I'm saying it's a probability, you already know from statistics and you already know from real life that pi is bounded between being 0 and 1. It can't be like more than 1 and it can't be below 0. This is a probability, right? So it's something that can happen between a probability from 0 all the way to 100%. Okay, so you can actually write it as, okay, my expectation of y given x is bounded between 0 and 1, and this is what we expect for a probability. So let's take an example. Let's see. Suppose that I have a data for yi that takes 1 if a family owns a house. Like you have a sample of families, let's say 50 families, and you're asking each and every family, do you own a house? If they say yes, 1. 0, I mean like if they say no, then it's 0. And so you either own or you don't own a house. Okay, so you have collected your data set, and this is like your yi, the responses like 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, whatever. Okay, so this is like your set of responses. And if I'm saying I have 50 families, then I have 50 rows of these. Okay, so suppose you collected this data set and you want to regress it on the factors affecting a family to own a house. Like what can affect you to own a house? Definitely one of the important factors is your income or the family's income, right? So you have a regression, which is yi hat is equal to beta naught plus beta 1 income plus ui, and this is your regression model. Okay, so let's keep it without the hat for now because it's the population regression line, and you actually want to estimate. Okay, and you get your estimated population regression line. And in terms of numbers, suppose that you got these numbers. Okay, so you got yi is equal to negative 0.9457 plus 0.1021, and this is income. And assume that this is in thousands, in thousands of dollars. Okay, so how can I interpret this? Again, as I told you before, whenever we are asked to interpret a model, we have to move in order. Like you take the intercept, the sign, the coefficient of the x, right? And you interpret the result. So this one is telling me that this one, which is the negative 0.9457, is the probability that a family with 0 income, because I have to set this equal to 0 to talk about the intercept. So this is at 0 income. The probability of owning a house is equal to negative 0.9457. Of course, we know that a probability can never be negative, okay? So in this situation, we treat the value as 0, and we conclude that with 0 income, there is a 0 probability that a family owns a house. So we can say probability, because it's close to the 0, right? And we don't take like absolute value. So this is the 0, and here is the negative part on the number line, and this is the positive part. Whenever I fall like here, whenever our value falls around the negative, then we just say, okay, let's approximate it to the closest one. Is it closer to the 0 or 1? It's closer to the 0. So we're gonna say, okay, the probability of owning a house equal to 0. So at 0 income, my probability of having a house or owning a house is equal to 0. Okay? And this kind of introduces us to one of the disadvantages of using the linear probability model, which is the fact that the probability sometimes is unexpected. I've never seen a probability which is negative, right? So in this situation, we just, as I said, if it is negative, then just say, okay, it's closer to the 0, then the probability is 0. Next, I want to find out what is the value, like suppose you have this question, what is the probability of owning a house if the family has 12,000 income per year? And remember, my unit of measurement is 1,000. So if I ask you this family has 12,000, then all what you need to do is to plug in here the value, which is 12, right? Because I said at the beginning that it's in thousands. So 12 means 12,000. So at income 12, the expectation, or y I hat, is equal to negative 0.9457 plus 0.1021 times 12. That's it. And you will get a value which is 0.2795. And this would imply that the probability of owning a house is equal to, you just multiply this times 100 and you add the symbol for percentages, is equal to 27.95%. So if the income of the family is 12,000 a year, the probability of owning a house is equal to 27.95%. Okay? Now, we can also try other values, like any value I give you for income, you just plug it in here, you multiply, you add or subtract, right? And you get the answer. So 2 more examples. At income equal 1, at income equal 24. Again, 1,000, 24,000. What is the predicted probability? So y I hat is equal to, so when you compute this one, you will find it as negative 0.84. All what you need to do is just go back here, you plug in 1 here, and then you add these 2 terms, okay? So you will get it as negative 0.84. Again, we are faced with the same problem because probability can never be negative. But again, we're gonna say, okay, at income of 1,000, the probability of owning a house is 0 because it's closer to the 0 as compared to the 1. What about at income of 24? I'm going to plug in 24 for income. I'm going to compute the y I hat, which is equal to the 1.5. Again, I know that a probability can never be, I know that based on what I've said before, a probability is bounded between 0 and 1. Like what's the probability of passing an exam? You're going to tell me it's something between 0 and 1. It could be even 0.7, which means that 70% I'm going to pass the midterm exam, or 100% I'm going to pass the midterm exam. But you will never be able to tell me it's 1.5% probability that I pass the exam, right? This is the answer here. It's 1.5 probability of owning a house. Okay, so in this situation, as I said, if it is closer to the 1, the probability is 100% of owning a house, because you're going to say, okay, the 1.5 is closer to the 1, so that means the probability is 1. Okay, so this is the problem with the linear probability model, is the fact that my expectation, remember this, you can call it the expectation of yi given xi, will not always be between 0 and 1, but might be 0, which is negative, or above 1. Okay, so when you look at the graph, I have here a graph of owning a house, and this graph has only 2 values, right? 0, 1. So when I collect my data from the, let's say, the sample of 50 families, I have people here and I have people here. I don't have anything in between, right? It's either here or there, yes or no. So based on the model I have, is I got a value which is sometimes in the negative part, right? Negative 0.9, and I actually got a value which is in the positive part. I mean, like it's positive, all the, like it's positive, I mean like above 1. So the linear probability model would give me something like that, right? It's linear, but has a problem, because I have values here which are negative, which are wrong. I have values here which are above 1, which are wrong. The only parts which are correct is anything that falls or include 0 and 1. Okay. So the other problem with the linear probability model is that we cannot rely on the R square, right? So the explanation of the model, I cannot rely on it, since we cannot, like this dependent variable is binary, right? Unless this dependent variable is a continuous variable, I can rely on the R square. But now, like if I'm looking at points here, definitely this is the actual observation, this is the estimated. I have a huge amount of error. And this amount of error is not related to my wrong prediction, but it's related to the fact that the structure of the model is only 1 or 0. So I cannot depend on the R square and say I have bad explanation, because actually this part is not touching any observation, right? It's not passing through any observation. Okay. Otherwise, all other coefficient tests, like when I say the t-test, the p-value, confidence interval, the f-test, joint test, carry on, right? Everything that we have done before is going to continue. It's the only fact that the estimated coefficients sometimes are negative, below 0, sometimes are above 1, and this is the main problem. But other than that, when I go back here and I say, okay, this is my model, in terms of interpretation, I'm just interpreting these coefficients the normal way we have learned. The t-statistic, if I have the standard error, I can interpret it the normal way we have learned it, and the same way for this one. Any question? Okay. So to address the problem above of probability exceeding 1 or lower than 0, we're going to introduce the other 2 options. The probit. So the probit model and the logit model are both used to overcome the problem of having probabilities which are negative and probabilities which are above 1. So they are basically designed to estimate the binary dependent variable, and they are always between 0 and less than 1, and this is going to be always, okay? So we don't have any problem with that. The probit model uses a certain type of probability. Like previously, like the example before, or the linear probability model, what we used to compute the probability was simply just the regular probability, right? I'm just giving you 80% chance that it's going to rain today, 90%, it's just the normal probability that we know. With the probit model, this probability is computed using the cumulative distribution function, or the CDF, okay? And the CDF is nothing new for you because you guys already have used it in computing the p-value, right? Using the standard normal distribution table, which you guys call it the Z table, right? And we have this notation for it, right? We have this notation phi of Z. So the main advantage of this model is that it overcomes the problem that we faced with the linear probability model, because by the end, I will never get a below 0 probability. I will never get an above 1 probability. And let me go back here. So whenever I want to compute any expectation, I need an outcome and I need a probability. So let's repeat that again. So here, the expectation of yi given xi is made out of outcomes and a probability, right? This probability is, we call it the CDF, and this probability is the rest, 1 minus phi of Z. Okay, so if I want to compute the expectation, then it's outcome times a probability. So the expectation would be equal to, I can write it in as a yi hat, it's the same. It's 1 times the phi of Z, right? Plus 0, right, which is the other part. 0 times the rest, 1 minus phi of Z. So that means, of course, this part is gone. Anything times 1 is the same. So this one is just phi of Z. So the probability, my expectation of y is computed based on the phi of Z. So that means my expectation is simply the phi of Z. So let's see that again using our same example. Okay, again, what's the probability that the family owns the house using the probit model? My probability now is made out of phi of Z, where Z is whatever my regression is, beta 1 plus beta 2 xi, and I actually should write it this way. Okay, so yi is simply equal to certain probability, and this probability, remember, this was multiplied times 1, and it was like the other term that was multiplied times 0. This is gone, and I can remove this, so I can write it this way. Okay, so this is just to remember that where we got this bracket from. Okay, now I said that this is a probability of owning a house, right? So I have values for this, I have value for this, and assume that this is income. So let me write it in the form of yi is equal to, based on the numbers I have from the previous example, 0.9457 plus 0.1021, right? And this is income. That's it, okay? So at income equal to 1,000, and since the unit of measurement is in thousands or 1, then I can plug in the 1 here, go to my table and get the probability. So let's see. So at income 1, just you plug in the 1, negative 0.9457 plus 0.1021 times 1, right? You just add and subtract, then this one is going to be equal to negative 0.84. Okay, so this one is, what's the probability of all the points that are less or equal to negative 0.84? I need this area. Okay, an equivalent way of writing it is, okay, what is the probability of 1 minus all the points which are less than the positive part? So these are equivalent, right? Because the 1 is everything under the graph, minus everything that is less than the 0.84, right? This is 0, the positive one, and I'm left with the same area, right? Which is because the graph is symmetric. So this is 0.84. So I can either use it this way or this way. It doesn't matter. Okay. Now, let's see if I have it this way. Okay, so let's let me clear this, since I already explained that they are equivalent. So it's up to you to choose which one. I prefer to use the first one, which is the negative, because like easier. So all I need to do is to go to my cumulative distribution table, and I have it somewhere here. Okay, so this is slide 7. Cumulative distribution table. Okay, as you can see, I have the Z here. I have it in your textbook, okay? So you look here, you see the Z. I need to look at the value, which is negative 0.84. I don't have it here, right? So it's in the next page. It ends, as you can see, it ends with negative 0.9. I need the second part of the table, okay, which is the first row right here. So I need this, and the second decimal is 4, so I need to go to 4. So this would give me the phi of negative 0.84. And I go here and I find that it's equal to this number, 0.2005. It's a probability, multiply it times 100. So the probability of owning the house is 20.05%. This is how you get it. Okay, so let's go back to our slide. Slide 7. Is it slide 7? Yes, here. Okay, so we found the probability to be equal to 0.2005 from the table, and this is the same as saying there is a 20.05 probability of owning a house having income of 1,000. I want you to remember that this computation extends to the multi-regression model. Like, as you can see here, I have only one X, but I can have a model in which I have other factors, right? I can have education. I can have whether the person works or not. I have age. All of these are factors that would affect the probability of owning a house. Okay, whether the person is married or not. and so on. So when you watch my other videos on the linear probability model, I have an expanded version of, I can't remember the example, was it work participation rate, I guess, or female work participation rate, and how many kids they have, and how it affects their work participation rate. So I want you to think of this video as a complement to the other videos on my binary dependent variable. Another thing that we can do is, if I ask you what is the effect on the probability of owning a house given, so this is the condition, okay, conditioned on income changed from $1,000 to 2,000. So is there any change in the probability of owning a house if your income increases by $1,000 or from 1,000 to 2,000? Unfortunately, it's not that easy as we used to have it. Like previously, if I give you this question, what you need to do is to plug in here 1,000 and you just analyze it. But remember, now our model is inside the function, right? So I have to have this function repeated twice, one for the before the change and one after the change, and get the difference and get the subtraction, okay? So I need to compute something like this. What is the change in the probability of owning a house, or probability that y is equal to 1 given certain level of income, okay? So this one is computed as y after the change, which is beta naught plus beta 1, new income, right, minus beta naught plus beta 1, old income. And if I subtract these two, then I would be able to answer the question. So let's plug in our numbers. So our numbers are negative 0.9457. I'm gonna have 2 here because it's in thousands. And the second part, when it was 1,000, we have already computed it here, so I don't have to do it again. It's right here, okay? So I'm just gonna write it, minus. Okay, so you need to look at the table again for negative 0.7415 minus, we already found this value from the table, 84. And if you check the table, you will find that this one is equal to 0.2266. And we already found this as 0.2005. Get the subtraction, 0.0261. The answer is 2.61% probability, increase in the probability of owning a house. So if income changes, remember every time I ask you a question, whether this is in your assignment, quiz, exam, whatever, you have to give me like a complete sentence, okay? Because I have seen many of you, they would just like write the number. Econometrics is not only about the number, it's about your analysis, right? It's about your interpretation. So a complete answer for this question would be, if income changes from 1,000 to 2,000, there would be a 2.61% probability of owning a house, okay? So this is, remember that you would need to write complete sentence in your analysis. As I said, the advantage of the probit model is that it would never give me any value. below 0 and no value above 1. So it's perfect. And looking at how this profit model graphically looks like, I know that my values are between 0 and 1. I would never ever have any values. So these are the values here. I would never ever have a profit model that is above 1. So it takes an S shape, and it's a smooth S shape that is bounded between the 0 and the 1. That's it. Okay, so with a linear model, and this is your income, and this is your probability Y, and this probability would only be between 0 and 1. And that's the advantage of the probability model. It takes an S shape, as you can see it here. And we're gonna also see it in our example. Okay, any question? Another similar approach, which is the Logit model. So the Logit model is similar to the probit model, but instead of using the CDF, right, we used to use the cumulative distribution function. This one uses the cumulative logistic function. Okay, so CLF. Okay, CLF. What is the cumulative logistic function? So in order to compute the probabilities of Y, I have an outcome 0 and 1. Each one has an attached probability. This probability is used to be computed by the CDF in the probability. Here, I'm going to compute it with the CLF, which is the cumulative distribution function. What is the cumulative distribution function? Cumulative logistic function. So the probability of Y equal 1 given X. I keep writing X, but you can make it actually an expanded version. I can have X1 income, I can have X2 for age, I can have X3 for education, I can have any number of X's. And of course, like, you don't get like hundreds of X's. You want to get like the balance between the best regressors that explain why, and at the meantime, you don't expand your model too much because you would run out of degrees of freedom. So you can have like a set of X's, the most important factors affecting Y, and you can like forget about the minor effect variables. And this probability is computed as F, so it takes the notation of F instead of the 5 previously. Okay, so F beta naught plus beta 1 X plus beta K X K. And the form of this logistic is simple. We can do it on the calculator because it's made out of an exponential function minus beta naught plus beta 1 X plus beta K X K. Okay. So as I said, currently there is no preference of Logit over probit models. They both give close results, but historically, before the development of the computers, there was a preference for the Logit because it's easy, right? I can easily compute this. I don't have to have a Stata to compute exponential function. I can just have my calculator, and even on my iPhone, for example, I can have an exponential function and compute the logistic distribution. So let's use the same example. Again, same question. What is the effect of a change in income from 1,000 to 2,000 on the probability of owning a house? Right? It's the same question. again, our computation is related to, I'm kind of want to compute an expectation of yi given the set of x's or the income I have, and any expectation is equal to the outcome times the probability. So my outcome is 1 multiplied times f of z, right? This is, I'm gonna call everything here as I used to, z, plus 0 times the rest. Now, this part is gone, so I'm actually want to compute f of z. So in order to do that, I want to compute one for the 1000, another for the 2000, and get the difference to get the change. So at income equal 1000, I'm going to plug in the 1, right? So I need to compute the y I hat is equal to the f of, remember the 1 when we computed it and it was like this number, so I'm gonna just use it because when you plug in 1, multiply, subtract, you will get this. So I'm just gonna use the same number, negative 0.84. Okay, which is equal to 1 over 1 plus e to the power of a negative. So the negative is already in the formula, negative 0.84. And negative times negative is just positive. So it's 1 over 1 plus e to the power of 0.84. And you will get it on your calculator is 0.3015. So at income of 1000, the probability is 30.15%. But this is not the question. Now, I want to do the same thing for income of 2000 and get the difference. So at income equal to 2000, the yi equals, where is it? Okay, I have the final answer. Just a second. Okay, so just compute it. So when you plug in 2, okay, where? I have it here. Okay, when we plugged in 2, we got this number. So I'm gonna just use the same number. So f of negative 0.7415, 1 over 1 plus e to the power of a negative 0.7415, which is equal to, you will find it as 0.32267. Now the question is about the change. So I have to take this and subtract it from this, right? So your answer would be the probability of owning a house for the change in income from 1000 to 2000 is 0.3267 minus 0.03, 0.3015, which is equal to 0.0211, right? In other words, if the income changes from 1000 to 2000, the probability of owning a house increases by 2.1%. So this is the answer of the question, right? So the probability of owning the house is going to increase by 2.11% if the person's income increases by 1000. So it's no more like straightforward as we used to have it. In a linear probability model, however, let's say the linear probability model, which is here, I can easily find the change, right? Just plug in the change 1000 and then you add and subtract, and that's easy because I don't see any phi or f. I mean, like I don't see any cumulative distribution function, logistic distribution function. It's just a linear model. anytime I have my coefficients inside a bracket, then it's no more easy to just analyze the changes. I would have to get this function before the change, after the change, and do the subtraction. Before we leave the model, I just want to say that in terms of the graph for the logit regression, is very similar to this S shape. However, it starts like a little bit higher and it ends a little bit lower. Okay, so it's supposed to be smooth. And that's why they would give us like a very close results. Okay, using any one of them is just like equivalent. It depends on your preference. Like if you're doing or reading a research paper that has a binary dependent variable, like you can either see it in terms of an estimation as a probit or logit. It's not like, I mean, it depends on the author preference. Okay. Okay. So I want you to note the following before we move to the example. Number one, the linear probability model, okay, cannot capture all the nonlinear nature of the population parameter. It has a disadvantage, so it cannot capture all the nonlinear nature of the population parameters. Disadvantage, probability might be greater than 1 or less than 0, which is wrong. Okay. The second thing to remember is that probit and logit, they both produce, okay, so as I said, okay, they produce similar results. So you can choose any one you prefer. Number 3. So remember that having estimated the probability using probit or logit, then I'm gonna get like a probability like that. So probability, let's say y equal to 1 or own a house given the income. And in the probit, this would be like, let's call it P for probit node, right? Plus beta hat, P for probit, 1 for the beta income. Okay, and this is the probit. For the logit, my probability of y own a house given income is equal to the logistic distribution, which has a notation of F, and the beta has L as a notation node. This is all just a notation, right? Plus beta L for logistic, 1 for the slope, or I can just have, and then income. An important thing to remember is that anytime, I'm just repeating what I said, anytime I have coefficients and variables inside brackets, then I cannot compare them. right? I cannot just look here and say this is bigger than this one. No. The only thing I can do is I can do the change, compute the change as we did, compute the change and compare the change as we did, 1000 to 2000. And then I'm going to compare the changes between the two models. For example, I have it here. So let's say, I can say, for example, that this is the probit, this is the logit, the change of x from 1 to 2 has produced 0.0261 here and 0.0211 here. This is what I can do. I can also say at x equal 1, this model gave me 0.2005, this model gave me 0.3015. This I can do, but I cannot look at this coefficient and directly compare it with this coefficient. I can only say they are both positive. This is the only thing that you can do, which is the direction of the relationship. Is it positive? Is it negative? And that's it. You cannot look what's inside the bracket in terms of magnitude of the effect, intercept or slope, and say this is bigger than this one. You have to compute the changes and compare the changes. Okay, what you can do is you look at the t-statistic and say, okay, this is significant, this is insignificant. Okay, this is something you can do. So significance, yes, you can do. Magnitude, you cannot unless you compute the changes. And then once you get the changes, then you can compare between the models. Okay, so I like having this introduction to the linear probability model. I want you to complement this introduction with the videos that you already have on the linear probability model. The other videos are giving you an example, showing you the Stata estimation, showing you the measures of fit for the linear probability model. So I want you to take all these videos together when you're studying because they complement each other. I think this video is just filling some gaps that might not be straightforward or clear in the videos that you already had. Any question? Make sure you watch the 3 other videos, okay? Because I can't stress enough how important are all these videos together. So you have one of the videos on the measures of fit, which is the linear probability 1, which is going through the count R-squared, the pseudo R-squared, the McFadden's R-squared, the wall test, the likelihood ratio test. These are all important. And you have one video on the Stata application, and which is again very important. Okay, what else? So let's see your slides. I just want to make sure that I have updated the slides that you guys have. So the slides, I updated it last night because I added a few other examples that I find interesting, and which again would complement the example of that I gave on the labor force participation rate for women, which is on one of my slides. Okay. Okay, just one thing I want to add for the notes I just remembered is, suppose that I want to compute, I'm just giving you an example, okay? Suppose that this is a probit and you can apply the same thing for the logit. And this is actually mentioned in one of my videos. Suppose I want to estimate the change in the probability of Y, okay? So let's say I said income is 2,000 and 1,000. So suppose that what's the effect from 1,000 income to 2,000, and you have seen that in order to answer this question, we plug in 1,000, we plug in 2,000, and we get the difference. Our example was easy because we had only one variable, right? We had only the probability of Y was a function of only income, okay? What if I have more than one factor? So what if I have income, I have age of the person, and I have years of education, okay? And this is just an example. So this is in years. Again, this is in years, the age of the person. And again, this is the probability of owning a house, right? And this is your income. So if I want to plug in 1 and 2 in a probability that is, oh, sorry, that is like beta naught plus beta 1 income plus beta 2 age plus beta 3 education, right? If I want to compute the change in the probability, then I would have to plug in here 1 times 1 and repeat with 2 and get the change. What I'm going to plug in here, like what are the values here? So if I have an expanded version of the model, I need to know certain values to plug here because these are inside the bracket, so they're gonna be with me anyways. So there are 2 options, as I mentioned in one of my videos. The options are, I'm going to give you some values, right? So given values. For example, I'm going to tell you age is equal to 27, education is equal to 10 years of schooling, okay? So what you do is, okay, I'm going to plug in here 1000, I'm going to put here 27, and I'm going to put here 10, and just have my phi. So you're gonna have just one number for this phi, and you look at the table. And then you repeat. When you repeat, you're going to have the 2. You plug in the 2. What I'm gonna use here, they are held constant. So I'm going to be using these values when the income is 1000, when the income is 2000. It's like I'm asking you, for a person who's 27 years of age and with 10 years of schooling, what is the change in the probability of owning a house if the income of this person increases from 1000 to 2000, right? So I will be giving you values for age and education, right? What if I'm not giving you any values? You basically compute the mean or averages. So you're going to plug in here for age and education. I'm not giving you any values. So you're going to look at the data set, compute the mean or average of age. So you're going to have here age bar for the average, education bar for the average. And again, remember, all my concern or my focus is on the effect of income, and I'm holding these 2 constant at their means, constant at their means. So your question would be, what is the effect of the increase in income from 1000 to 2000, right, on the probability of owning a house, holding all other variables at their mean? So this information would tell you, okay, go ahead and compute the means of these variables and just plug them in, okay? And this is going to be like important if I have an expanded version of the modeling, not just income. Okay. So what we're going to do is let me show you a Stata application. So the Stata application, I sent you a data set on charity, right? And what is the data set? What's the story? The story is simply saying that you're sending like mails to people to contribute to certain donations, and you have one of 2 options. People would respond or they will not. You don't have anything in between, right? So the charity data set, which is our practice today, has a story, which is the people respond or not, okay? So respond, it's gonna take 1 if yes, if the person responds, let's say you're asking them to contribute to a charity with a gift. So 1, if yes, they contribute with the gift. 0, if not. That's it. So your response is a function of a set of x's, right? Let's say the amount of gift, right? Let's say the average past gifts. Let's say another dummy. Remember I told you the x could be a binary, we don't care. So this binary is respond last, which means it's gonna take 1. If the person responded last year, so it's most likely if the person responded last year and sent donation or a charity, they will not respond next year, right? So if the person is already responding, then he might not skip the next year. So respond or responded last year, since last year, and 0 not. Okay, so you have the data description already posted for you, and then you have the data. Have you downloaded the data set? Then have you downloaded the data set? Okay, so you guys have the data set description. Different versions, DTA and Excel. Okay, so I think I have it somewhere here. Okay, so this is a Stata Practice, and it's based on the charity DTA file. You can read the description in charity TXT, which is a text file. And I'm assuming that you guys have already watched the video on the measures of fit, which is the binary dependent variable part 1. And as we said in the video, that the estimation of a linear probability model is simply a regress of y, x1, x2, all right? For the probit model is simply, I'm gonna remove the reg and just type probit y, x1, x2. For the logit, again, logit y, x1, x2, or x3 and x4, depending on how many regressors I'm asking you to estimate. Okay, so this practice, I'm asking you to install the fit. The FitStat actually package is very, very handy, because it would give me all the measures of fit that we have discussed. Okay, it would give me the pseudo R square, it would give me the count R square, the McFadden's R square, the likelihood function test, and so on. So if you don't have it, right, you can type SSC install FitStat, and this is just under the assumption that you can type this directly into your Stata command terminal. Okay, otherwise most likely you guys have it. And once you have this package, you can start working. Okay, I want you to respond. So this is my dependent variable on weeks last. Okay, what is weeks last? Is the number of weeks since last response. Okay, and then gift last. Gift last is the amount of most recent gift. Res last, which is binary dependent variable that takes 1 or 0. So this one would take 1 if responded to most recent mailing, and 0 if not. And here I just need a linear probability model. And this one would be like a simple regress command, as I'm gonna show you. After you're done, you're asked to use the Stata summary to find the average values. Okay, I told you like we have two options when we're working with probit and logit models. I can either give you certain values of other regressors, or I ask you to compute at the mean, right? So computing at the mean that you need to compute the averages. Okay, once you get the averages of weeks last, gift last, right? Then you're done with question 3. Number 4, you're asked to regress your y on x1, x2, x3 using a probit linear probability model. Okay? And you are asked to, once you do the regression, you're asked to estimate the difference in probability that a subject responds with a gift when asked, given, and this is information is very important, given the last mailing was successful or not. Okay, and then we're gonna use the average values of last week and gift last. I already told you that these are computed here. So weeks last, and I'm going to be taking this variable and computing the probability for 2 cases. One when it's taking 1, and the other when it's taking 0. Okay, successful or not. Once we do so, we're going to repeat it for the logit model. So if you're done with that, you just copy paste and repeat it for the logit model. Okay, so I took like a screenshot from the do file, and I'm going also to show it to you like now. So I just find it easy to show it to you here, and then we're gonna move to the actual Stata. Okay, so you start with creating your log file, because you are supposed to upload it after you're done, right, on your Dropbox. You call your DTA file or Excel file, whatever you like, set more off, okay? And then the linear probability model, assuming a robust standard error as given in the question, you're going to just a regular regress command, the Y on the 3 axis, and you can either type R or robust. This would give you the estimation results. Now, the question is asking you to compute the means of variables or the averages. So the first one you're asked to do is you want to do that for weeks last, and I'm asking Stata to return the list, and I'm going to create a variable, call it weeks last mean, which is going to the means which is saved in the background of Stata, and save it in a variable which I decided to call weeks last underscore mean. Okay, and I'm going to do the same for, actually, just to let you know that you can actually type sum week last gift last. This would give you like a table with the means and standard error and minimum and maximum, and you will see the means. But this way is nicer because it makes our life easy in presenting the results. Okay, I like this way, which is extracting the averages out. We're going to repeat the same for the mean of gift last and give it a certain name, which is gift last. Okay. We're going to compute the probability that responded last is no, or responded last is yes. P0 and P1 are just names that I decided to give. You can call it your name 0, your name 1. It doesn't matter. But it's like easier to call it P0 and P1. And this P0 and P1 is the, it's going to take the intercept of the previous regression. And remember, anytime I want to extract the intercept, I go to the matrix of coefficient, which is underscore B and square brackets. And I write here the name of the variable that it exactly appears in the regression. As you can see, I don't have here the constant term, but it's saved somewhere in the background as underscore constant, which is the intercept. So you're extracting it, taking the coefficient or the beta of weeks last, multiplying times its average. I'm setting it at the mean, doing the same with gift last, multiply it times the mean. And this is my coefficient, I mean like variable of interest, which is respond last, right? And the respond last, which is the one, it takes 1 if responded to the most recent mailing and 0 if not. So here, if the person did not respond to the last mailing, and here, what's the probability that he would respond now, given that he did not respond to the very recent mailing, okay? And I'm gonna do the same, just whatever you write here, copy paste, it's exactly the same. And the only thing that's gonna change is the 1. What's the probability that the person responds given that he or she responded to the most recent mailing? And the difference between these two would give me the answer. What's the change in the probability of response given that the person responded to the most recent mailing? So as you can see here, I like to display my commands or answers. So DIS is a display. You can type either display or DIS or even D. No, D would give you the describe, sorry. So DIS, the shortest you can go. And then between quotation, write whatever you like, okay? This is your answer. And I told you that anytime I'm asking you a question, don't just throw the number. In econometrics, we're not just about numbers, we are about analysis. So you have to answer the question in a complete sentence. Otherwise, as you have seen in my grading for your assignment 1 and 2, you lose credits if you don't give me a complete sentence. Just a number, it doesn't make sense or doesn't make complete sense to me. So you have to tell me in a complete sentence, which is actually derived from the question. You go to the question, okay, what she's asking me? Okay, she's asking me, okay, this is the complete sentence. The probability of someone who didn't respond at most recent mailing at means is the normal probability, which is actually the phi of Z, and the Z here is the P naught, which is computed from here, certain value given from here. And the probability of someone who did respond at most recent mail, then it's the probability that this one is equal to 1. And then the difference in probability is these two, the change. And this is what we want, okay? Now, as you can see, this is a computation of the linear probability model. Is just like or actually this question doesn't ask you for the linear, right? Does it? Oh, yes. Sorry. Yes, it does. And it's right here. Okay, we have already mentioned that. Okay. Remember that the question asked you for robust and robust. So you're assuming that this is a heteroscedastic model. I'm talking about different people, their behavior to respond. I don't think that they are homogeneous group, so most likely it's a heterogeneous group. And as I said, in most of cross-sectional applications, you're safer to use heterogeneous model, or I mean heteroscedastic standard error. You're safer to assume heterogeneous model, and you're safer to use heteroscedastic standard error. Next, whatever you have done here for the probit is just going to be repeated for the logit. Okay, in terms of the regression, all what you need to do is just remove the probit and type logit. So here what we have is the continuation of the code, right? Before I go to the logit, the fit stat command would actually compute for you all the measures of fit. Okay, so it'll take you to the count R square, the McFadden's R square, the adjusted McFadden's R square, the likelihood ratio test, and so on. Okay, and now the fit stat difference would give you the difference between a model that has all the regressors versus a model that has just the intercept. Okay, and if you don't understand what I'm saying, just refer to the video, which is about the bind-dependent variable part 1. The bind-dependent variable part 1 is taking you through all the measures of fit and what is the meaning of comparing two models, one that has all the regressors versus one that has just the intercept. So the fit stat is all about the measures of fit. Now, we're going to repeat the same. Okay, so we're going to use the logit. Again, we are using the other x's at their means. We're using 1 and 0 here. And we are going to compute the logistic distribution function. Remember that you would have to call different names, and you're going to display using the logistic distribution. Okay, one time when it's equal to 0, another time when it's equal to 1, and the difference between the two. Okay. I'm not sure, did I ask you anything about the test PARM? Let me see. Can you remember that I asked you anything about the test PRM? Let me see. I didn't, but it's an additional information. So let's say if I did ask you, for example, can you compute the statistical joint significance of the 3 regressors, then you would do an F test. Okay, it's not given, I'm not asking you to do that, but it seems an additional information. Any question? Okay, so let me share my Stata. Okay. Dan, you have any question? Okay, so what we have here is the code that I had like screenshots from. Okay, and okay, all right, so let's see. Okay, so now what I have here is I already imported the data set, and it's here, the respond. Actually, whatever you see here, you already have it in your text file, which I sent you guys. which is already on the course site. So all the abbreviations and their labels here, okay, their definitions are here, okay. So linear probability model is simply a regress command, okay. So wow, it's just sometimes my Stata is just okay. I would have to restart my computer to get a nicer table. But anyways, I think we can read it. So this is the coefficient of weeks last. This is the coefficient of gift last, the coefficient of the last, whether the person last responded or not, okay, and so on. There is a negative coefficient for the weeks last, which is based on the description. Weeks last means that the number of weeks that since the person last responded. And of course, if the person responded last year versus another person who responded last week, the further I go in the past that the person did not respond, the most likely that the person will not respond. And that's why the higher this number, the most likely that the person would not respond. And okay, so what we have here is the computation of the means. Okay, so we got the means for the variable. Okay, and what we are interested in, remember, is this one. So that's why we are extracting it here and naming it anything. Okay, so I'm naming it gift last mean because it's easier to remember. And next, we're doing the same thing for week last. Okay, we did already week last. Okay, week last name. And then the probit model. Okay, so for the probit model, what we got is the coefficients here. Remember, you cannot look at these coefficients and interpret the results. We cannot do that. Okay, so what we can do is just say negative or positive, or that's it, statistically significant or not, yes. But we cannot just use these coefficients because remember, as I said, these are inside a function, cumulative distribution function, right? So I cannot talk about these coefficients or the impact of whether the person responded last, then it's equal to 1 and multiply and just look at this coefficient. No, we have to multiply each one at the mean and then take the difference between this variable being 1 versus this variable being 0. And in order to do that, we have to create a scalar, right? And display our results. And when we display our results, it makes our presentation nicer. So the probability for someone who didn't respond at most recent mailing at the means is 32.74 or 75 approximately %. The probability for someone who did respond at most recent mailing is most likely is going to respond again, so it's higher. The change in the probability is around 16.75% probability between not responding and responding. Okay. Okay. Computing the fit stat, which is all the measures of fit as I have explained in the video, right? And remember, these are the comparison between a model that has, for example, the maximum likelihood R-square is the difference between a model that has all the variables included as compared with a model that has just the intercept. Okay, the McFadden's R-square is here. The count R square is the probability that how many times I can see the Y equal 1, which is the Y, which is the respond, right? So how many times I can see it equal to 1, which is 67%, okay? Next, we can repeat for the logit model, right? Just repeat, different probabilities computed. Okay, and again, you can see here that with the probability that the person respond, given that he did not respond at most recent mail, is 32.60 approximately. Now, if he did respond, then it's higher probability, it's about 49%. The difference in probability is 16.44. It's very close to what we got for the logit, the probit model. We got a 16.75 probability versus here we got 16.44, which is very close. Okay, and that's why we said, which one are we gonna use? Is it probit or logit? It depends on what you prefer, because by the end, when you tell me 16.44 versus 16.75, it's actually around the same or very, very close result, right? And that's why we said, in terms of preference, it all depends on what you like. Okay? Any question? Okay. Then have you done the practice of last week? Can you open the mic? Because I just want to double check that my mic is working.
Hello.
Hi, Dan. Have you done the practice of last week, which is about the sequential hypothesis test? Remember?
I did the homework.
Yeah, the homework. I'm saying the in-class practice.
From last week.
Mm-hmm.
I probably tried it, but
Okay. So let me, since we are here, so let me, this one, which is,
I don't have it saved because I use the virtual lab.
so when you have the virtual app, you cannot save your do file?
No.
Wow, that's right, double the work or maybe more, because every time you would have to create a do file from scratch. You
Yeah,
might
it makes sense.
you might explore the possibility of getting the student version of Stata. I'm not sure how much is it now. Maybe they offer the discount for because everybody now is like, most people are are virtually learning, so maybe they offered any discount. So maybe check this, because this would be like a very beneficial for you if you're like creating new files and they are gone after you're done. This is like huge work. Right? The best thing about do files, as you have seen last semester, is that you create one do file and then you're most likely gonna copy it and paste it for other applications, changing the name of the data set that you're using and the new commands that you're adding, right? So once you learn one, it's easy to replicate. Okay, so let me show it to you since we are here before I leave Stata. So this one, we were asked to compute okay, just want to maximize this. Okay, so we were asked to compute a model using robust standard error by regressing log wage on education, age, non-white, union, female. And I'm asking, what is the exact increase? Remember the word exact versus approximate, because we have two ways of computing a change, either exact or approximate. When I have as in point number one, the model is linear, so actually the choice between exact and approximate, it's the same. But it makes a huge difference when I come to a quadratic model. Okay, so if I'm talking about a quadratic model, then I have to make sure that I check whether the question is asking me to compute an exact or an approximate. And the good news is, if the change is small, as I can see here, 25 to 26 years of age, which is the same as here. If the change is small, which is like here, 1 unit, then the difference between exact and approximate would be very, very, very close. But if the change is, let's say, between 25 and 35 years of age, which is 10 years, or an increase by 10 years, then I would find the difference between the exact versus the approximate change. Okay, so anytime I have a quadratic model, I have to make sure I see whether we are talking about an exact or approximate. So here we have it, where is it, like here, okay, and what we're doing is, let me minimize this one. So you are asked to get the data set, okay, and then point A is about just the log linear model. You are asked to come to regress the log of wage on education, age, non-linear, non-white, I'm sorry, non-white, union, female, using robust standard error. Anytime I'm like working with the regress command, I prefer to extract the coefficients from the beta matrix. So I go to the beta matrix and extract the coefficient I want. So here, after I'm done, because the question is about age, I'm going to extract the age coefficient and call it anything I like. I'm sure that it's convenient for us to remember that this coefficient is called beta underscore age. Okay, and the first part, which is the display, is the answer to your question. The question doesn't ask you about 51 to 50, but you have it here as extra information. So remember, this is a log linear in age, and actually in every other regressor. So when I ask you from 25 to 26, remember, if this is log, then my answer has to be in percentages. And I have to multiply the coefficient times 100, as I did explain in the previous topic on log models. So to do that, okay, let me first clear what we have. So let's get the new data set. Once I have the new data set, you can do the describe and summarize. I don't need it now. I'm going to generate the variable L wage. I always use L for log. Do the regress with robust standard error, extract the coefficient, use it in my statement to answer the question, because if you just give me a number, you will lose credit. So make sure that you get a sentence out of the question, right? As age increases from 25 to 26, the hourly wage increases by beta times 100, and add the percentage symbol. You can actually look here and get the answer, right? So you just take this number, multiply it times 100, add the percentage symbol. But to have a nicer presentation of your results and the question in a midterm or in a homework, I might ask you to extract the coefficient, right? So if I'm asking you, then you basically extract it and you will get like a nice sentence, right? As age increases from 25 to 26, average hourly wage increase by this number, and you add the percentage symbol, and that's it. Okay, so this is an extra information, as I said. Like, I didn't ask you about 50 to 51, but remember that it's a linear model, so you would expect to get the same slope, right? It's the same anywhere on the line. It's a straight line. The slope is the same everywhere. So if I ask you from 25 to 26, 50 to 51, 60 to 65, I will get the same number, right? Because it's a linear model. And the intention of this additional information is to show you that at low levels of age or at high levels of age, the impact is the same. It's a linear model. Now, the question is asking you to do the hypothesis test. So question 2, use sequential hypothesis test to determine the degree of polynomial in the age variable. So I'm focused on a certain variable, which is the age variable. And I'm using this variable to perform the sequential hypothesis test. And as I said, when I was explaining the sequential hypothesis test is to start with R4. This is our default, even if I'm not telling you. Okay, so you start with R4 and keep moving to a smaller model, R4, R3, R2, linear. To do so, I need to add these these variables. I need to have h squared, h to the power 3 or cubic, and h to the power 4. So I do generate, and Dan was asking me what is generate before, and like I think last week, generate is just create. Right? I'm creating a new variable, the square of h, the cube of h, and h to the power 4. And then once, let me just minimize. So once you generate, remember, you will get them here. You have 3 additional variables created in your variables set. Now I'm going to perform the sequential hypothesis test. Have a model up to 4, a model up to 3, a model up to square, and check. Go from big to small. Then let's go back here from the big to small. It's right here. Remember, we're using robust standard error all the way because the question is saying that. So up to 4. All I need to do with a sequential, look at the statistical significance of H4. It's very, very small t statistic. Easier, look at the P. There is a 59.7% probability that H4 is equal to 0, right? So you fail to reject the null. That means H4 is insignificant, statistically insignificant. You drop it, you go to a smaller model, H cube. Look at the statistical significance. Again, it's insignificant. Why? See here, the p-value 13.6 exceeds all conventional levels, 10, 5, and 1%, right? So again, drop it, go to a smaller model. Check H square, statistically significant. There is a 0 probability that the null is true. You reject the null hypothesis and you conclude that my model is quadratic. So a sequential hypothesis test is moving in order from a big to small model. And as I said, some people would prefer to go from small to big, but I prefer to go from big to small model. All right. The next question, use block test to determine. I'm going to use a block test, which is simply an F test, to determine if the model is polynomial of degree 4 or linear. So in other words, when I go here, block test, I need to compare a model that has up to 4 powers and check if it is power 4 or just linear. In other words, I want to make these equal to 0 and see if they are actually equal to 0 or not. Because if these are equal to 0, then my model is linear, right? I only have H. So your test, your block test, or your F test is on H squared, H cubed, H to the power 4. And you perform the F test, right? So you perform the F test and you get the results right here. There is a 0 probability that these are equal to 0, okay? Or you reject the null hypothesis and say that my model is non-linear than linear, okay? So as I said before, the block test is it's just giving you a general picture, right? It's just telling you, okay, your model is not linear, but it's not specifically telling you, is it 4, 3, or 2? So that's why I personally prefer to do the sequential hypothesis test, because it would tell me more specifically, okay, nonlinear of what degree, okay? Next, your question is saying, use the log quadratic. The age variable, so that means I need to add the square term of age. That's it. So I'm going to use log quadratic model, which we have already checked that our model is a log quadratic. This is the best fit we have. And we want to compute the exact change or increase in log wage from 25 to 26, if age increases from 25 to 26. Okay, so to do that, we are going to, okay, this is a turnaround point. Didn't ask about the turnaround, so I'm going to come back to this. So using the R2, we estimate the exact effect of the increase from 25 to 26. I'm going to have a regression log quadratic, okay? I'm going to extract the coefficients. So you have it like that, and then you basically extract the coefficients. And once you extract the coefficients, you can use it in order to answer your question, okay? So you're going to generate a variable, call it anything you like. I'm calling it something I would remember. So I'm generating a variable called log wage age 25, 26. And this would give me the impact of the increase from 25 to 26 on log wage. And remember, this is a log quadratic. So whatever value I get, I have to multiply it times 100 and add the percentage symbol, okay? So just want to have the data here open right here, and this is my do. And okay, so we have extracted the coefficients. We're going to use them to write a nice sentence. And okay, if age increased from 25 to 26, hourly wage would increase by about 3.248, whatever this number is. Okay, you can approximate percent. Okay, you can see this part is so close. You can actually add a space here so that you have a nicer presentation, and the same goes here. Again, as I told you, this is extra information. I didn't ask you about 50 to 51, but since we're here, let me show you the extra information. So from 50 to 51, we're no more getting the same answer, right? Previously, we used to have a constant slope. Now it's no more the case. As I can see, 20 to 25, 25 to 26 is giving me an increase in wage by about 25%. Now, if the person's age increase from 50 to 51, the hourly wage would increase. It actually is going to decrease. It's a negative, right? I should write change by negative 0.25 or 26%, 0.26%. Okay, so would change because it's not going to increase. Okay, might be also interesting to know what is the turnaround point. If I have a quadratic model, I can see that. Let's just show it to you here again. And I have a quadratic model. What is the result telling me? Age has a positive impact on the percentage change in wage. However, this positive impact is decreasing at a rate of 2 times this number. Why 2 times? You just need to go back to the equation of our derivative of log wage versus age. What is the first derivative of this equation with respect to age? When it comes to the age squared, then I have 2 times the beta, right? So age has a positive impact of this amount. However, this positive impact is decreasing at the rate of 2 times this number. So we have something called a turnaround point, or the cutoff point, that we need to determine. The turnaround point, based on our lecture and the videos on the polynomial models, is computed as the absolute value of beta age, which is the coefficient of the linear term, divided times 2 times the coefficient of the age squared, which we have already extracted them from here. And it's very helpful to get to extract the coefficients, because we can write a sentence with the answer. The turnaround value of age is 68 years of age. And that makes a lot of sense, because in our previous question, when we were talking about 50 to 51, it's after the turnaround point of about 49. So the turnaround point is telling me after the age of 48.68 approximately, the effect is negative. Any point below 48, or any person below 48.68 would have a positive impact on wage. And that's what we see here. 50 to 51 are above the cutoff point, or the turnaround point, and that's why we're getting a negative result. This one is below the cutoff or turnaround point, and we're getting a positive result. And that's very, very important, because a turnaround point will give me the point at which my relationship starts from a certain sign to the other sign, from positive and being negative, or negative being positive. Like, for example, a cost minimization problem, I would have the linear term being negative, but the positive term is being positive. The nonlinear term is being positive. And at this point, again, I would need to compute the turnaround point. Okay, then you have any question?
I'm good.
Okay, great. So this is about the practice that we had for last week, the in-class practice. What we're gonna do next? I have so many things to do actually, but they are all like applications, which is good, because I'm giving you like more and more applications. So I'm just trying to think which one should I start with first. So let me start with going through the example that you guys have on your slides, okay? And again, I updated the slides, so you should find it on the course site. All right. Okay, we're done with that. So let me go to your slides. The slides are very important, so I want you guys to go through all the slides. Let me just go through the application. It's an interesting example. Okay. Before I start this one, let me take a 5 minutes or 10 minutes break. So, okay, so I'll be back at 2:39. Now it's 2:29. So I'll be back at 2:39, okay? You can take a break. You can switch off your mic. And I'll be back in 10 minutes. Okay, so let's start. So on your slides, okay, you have a really nice example, which is about the mortgage application to the Boston HMDA data. And this is like our topic is a binary dependent variable. So as you might expect, we talk about mortgage application, and with a mortgage application, you have two options. You go to the bank and you apply for a mortgage, and you either accept or deny. Okay, so it's one of two things that can happen. And accordingly this is actually something done like in real life. So each bank has like a research department, and this research department is collecting data about their clients. And a great source of information is the application, right? You write down your application, write down your income, your credit score, whether you have applied previously in the past, whether you have been denied before in the past. You also apply, you actually also write information about your payment to income ratio, right? Your education, your race, right? So maybe your religion, and some of these factors are actually insignificant, and some of these factors are important and matters. So the focus of this application is on race, and it's asking this question: is there a differential access to the bank mortgages or to home loans by race? Like they do have here the race of black and white, so they don't have anything else. Okay, black and white, and they want to see if the applicant being black, does this increases the chance of being denied from the application? Okay, or if the person is white, has a higher or lower chance of being denied. And the data set is collected for 2 years. Okay, like the normal process, you go to the bank, you fill out an application using information which is personal and financial. You go to the loan officer would decide, and they actually do have like a program in the background that where they would plug in your information and they would come back and say yes or no. Okay, or they might come and ask you, you need to increase your income to this certain level to be accepted. Okay, the key financial variables available are the payment to income ratio, how many payments you do per month versus your income. Okay, so let's say you have other mortgage, or you pay for a car lease, or you pay for electricity and water and everything else. Okay, you pay for your kids' education. Anything that you pay has to be included as versus your income, and based on this ratio they would determine whether, and of course if the higher this ratio, the higher the probability of being denied from the mortgage application. And then housing expenses to income ratio, the loan to value ratio, right? The higher the loan to the value of the house, the higher the probability of being denied. The bad the credit history, the higher the probability of being denied. The loan to value ratio has two variables here, whether it's above 80 or above 95. And of course, above 95 has a higher chance of being denied. And then the credit score, of course, matters. Okay, when you read your textbook, and this is in I don't have the page. I think it's page 367 or 366. You have like all the detailed definitions of each and every variable. So it will give you an idea. Okay, credit score, is it the higher the credit score, the bad, or is it the higher the credit score, the worse? Because yes, we understand like in normal life, the higher the credit score, the better. But actually, when you see how they are defining this indicative variable, it's taking, let's see. Okay, here. The mortgage credit score, it takes 1 if you don't have any late mortgage payments. It takes 2 if no mortgage payment history. It takes 4 if more than 2 late mortgage payments. So according to their definition, the higher the mortgage credit score, the worse. Okay, so just don't get mixed up between what we define it in real life and how the variable is defined in the study. Okay, so this is exactly on page 366, and you can check it and when you read the example. Okay, and then let's see. Okay, see, this is all the different variables. You have this is our dependent variable. No, wait, this is not our dependent variable. Where is our dependent? Oh, they don't have it. Okay, so this one, this is our dependent variable. Deny being 1. So this is the probability of college application being denied, whether you're applying for a loan for a condo or just a house, right? Or otherwise, whether the person applicant is Black, it takes a dummy variable. Okay, this is our dependent variable actually. This is the Y. Okay, it takes 1 if denied and 0 otherwise, and so many other factors. And let's see. This table has the linear probability model in column 1, the logit model in column 2, the probit model in column 3. And then starting from 4 onwards, it's just a probit model, okay? Or the author could have used a logit model, doesn't matter. But definitely not an LPM, because the LPM has its own disadvantages. So let's look here. Remember, I can compare the signs, like being Black increases the probability of deny by 8.4%. Like if the person is Black, there's an 8.4% chance of being denied. And this is higher than a white applicant, because this variable would take 0 if the person is white. A 1 unit increase in the payment to income ratio. Remember, this is a ratio that goes from 0 to 1. Okay, so the unit here is going to be like a 0.1. Okay, so a 1 unit increase implies an increase in the probability of deny by 0.1 times this. Okay, and it's a ratio, that's why I'm taking 0.1. All right, housing expenses, it's insignificant. So anything that is statistically insignificant, as you see the stars here, the star here is telling me it's, the 2 stars is 5% significance. Let me see the definitions, because sometimes they do change. Okay, it's right here. The 1 star is the 5%, the 2 stars is the 1%. They don't have anything, it seems, in this table, they don't have anything that has 10%. So that's why the definition of the 1 star is the 5. So anything that is insignificant, don't worry about analyzing it, because I would see some students, they go ahead and say housing to expense to income ratio, the 1 unit increase reduces the probability of deny by 4.8%. No, don't mention anything. If the coefficient is statistically insignificant, just forget about it. Don't even analyze the sign, because based on the definition of hypothesis test, it's indifferent from 0. So I really don't care whether it's negative or positive. It's actually indifferent from 0. Okay. Median loan to value ratio, if the loan is between 80 to 95% of the house, or yes, of the house ratio, then the probability of deny increases by 3.1%. However, it increases up to 18.9%, which is almost 19%, if the loan increases, if the loan is higher than or equal to 95%, okay, of the house value. Consumer credit score, as I told you, when you read the definition, let me go back here, you have it actually right here. Consumer credit score, the higher, the worse. Here you have no slow payments or delinquencies. Here you have delinquent credit history with payments 90 days overdue. So the higher this variable, the worse. okay? Same goes here. The higher the mortgage credit score, the worse. The higher, the worse. No, actually, this is not. This is one if public record of credit problems. Here, if you have a problem, here, if you don't, okay? But this variable and this variable, the higher, the lower, the worse. So that's why we would expect a positive significant, because the higher the consumer credit score, the worse is the credit score, and the higher the probability of deny by 3.1%. Again, insignificant, don't worry about analyzing. Just say the coefficient is statistically insignificant. Just pass it. Next, public bad credit. If the person has a public bad credit, this increases the probability of being denied from the mortgage application by 19.7%, which is really high. Denied from mortgage insurance, if you were previously denied from mortgage insurance, then 70.2% that you would be also denied from the mortgage application, okay? As you can see, this is a linear, everything here in column 1 is a linear, so I can just take these coefficients and analyze it as I'm saying. With the logit and the probit, okay? Logit and probit, it's not that easy, because with the logit and the probit models, it's I need to plug in these values into either the logistic function or the cumulative distribution function and do that change in order to be able to analyze these numbers, okay? So all what you can do is just say, okay, this is statistically significant and positive, being black increases. Don't say anything about this 38.9 because it has to be inside the function. Don't say anything about 68.8 because it has to be inside the logistic function. All what you can say is black increases because it's positive. The probability of deny is statistically significant. The loan to value ratio has a positive effect. Consumer credit score, when it's worse, increases the probability of deny. Same goes here. And public credit score, bad public credit score, increases the probability of deny. And same goes with the mortgage insurance. Okay, so in column 4, 5, and 6, the author just focused on one of the methodologies, and of course, it's not linear probability model. It's either or probit or logit, and adding further interaction terms and just trying to have a sensitivity. We call it a sensitivity analysis because you want to see how your model performs if I add multiple other variables. So let's see here in the column 4, what's added is whether the person is single increases the probability that you're denied. Like being married, most likely, like it shows like you're responsible, have more stable social relations. So most likely it decreases the probability of deny. So if you're single, it increases the probability of deny. Education matters, right? If you have a high school diploma versus no school, education decreases the probability of being denied. Unemployment rate doesn't show any statistical significance. So what's going on in the economy doesn't really affect my application of being denied, as you might expect. Whether the loan application is about a certain big house or just a condo, or otherwise, I should say, whether it's about a condo or otherwise doesn't really matter on the probability of being denied, okay? Okay, we said education matters. We said single or social condition matters. What about if you want to check some interaction terms? Okay, so what is the interaction term here? Here you want to see, like in these two, actually not one of them, these two are about a certain question. Are there different standards applied in evaluating the payment to income ratio and the house expense to income ratio for Blacks? Is there any different standard given to Blacks? if there is actually discrimination, I would expect these to be statistically significant. However, I see the answer is no. And as I said, econometrics is all about analysis, interpretation. So what you can say is the answer is that there is no statistical significant difference in standards applied in evaluating the payment to income ratio and house expense to blacks versus whites. This is the intercept, okay? Additional credit rating indicators, they were not added. Here they were added, yes or no, and just, you know, you're doing a sensitivity analysis, you keep throwing in some regressors and see how your model performs. And the most important thing is when you keep on doing sensitivity analysis, you check that your main model is statistically significant. As you can see, rates turn out to be statistically insignificant when you added the, when you removed the additional rating indicators. So that means you really need to have your additional rating indicators right here so that you can have the best model. So I would say based on this, this is your best model in which you have your main variable is statistically significant. You're testing the main economic or financial variables. If these are insignificant, then you just remove them from the model. Okay, and this would be your best model. You can actually do some F-tests. The F-test is anytime I do have any interaction terms, I would be interested to see whether this interaction is significant or not. Okay, so what we have here is I want to check whether being single, educated, and the state of the economy in terms of industry unemployment rate, the three together are equal to 0. This is your null hypothesis. Whether being single is 0. High school diploma is 0. Like whether all these do not matter. What the answer is, look at the p-value, is easier to interpret. There is almost a 0 probability that these are equal to 0. In other words, leave them in the regression, despite the fact that this is turned out to be insignificant. Remember that the F statistic allows you to have one or more coefficient to be statistically insignificant. Okay. What else? Additional credit rating indicator variables. Actually, this is showing us that there is a 29.1% probability that they are equal 0. So actually, you know what? Having them is not statistically significant. You can actually remove them. Okay, so you can remove them based on this test. What about race interactions and blacks? Okay, there is a 0% probability that these are equal to 0. Race interaction only, there is a 76.6% probability that these are equal to 0. So that's why I really, if these two are insignificant, then just remove them. Okay, and this is what this test is telling me. There is a 76.6% probability of having a different standards for blacks versus whites. This one is very important. Why? Because it's showing me the difference in predicted probability of deny for white versus black. I know that the very first one is easy to find because I can get it right from here. It's right here, right? So you get it multiplied times 100 and the answer is there. I cannot do this with this number. I cannot do this with this number because these are inside a function. So what the author did for us is he has computed for us the probability by inserting one time black equal 1 and another time black is equal to 0 and getting the change in the probability of deny. Okay, so they got that this is a 6% probability of deny when the person is black versus white. There is an increase of 7.1% probability of deny if the person is black versus white using probit model, using logit model, isn't it? Logit, yes. Okay, so despite the fact that the first one is easy just to extract from the table, it's right here for us, and these are based on some computations in the background that you can actually replicate and try and make sure that you're getting the same answer. And the same goes here. Every time, black 1 times 0, 1, 0, 1, and you're getting the answers. I would say don't use this one because actually the race coefficient is insignificant. So don't go with number 6 at all because your main focus, which is black, is insignificant. So there is no point of analyzing it and plugging in 1 and 0 for it for model 6. Okay, so just analyze a coefficient when it is statistically significant. If it is statistically insignificant, do not worry about its impact, do not worry about its magnitude, do not worry about its sign because it's insignificant, right? As we did here. All this row, this whole row is insignificant, forget about it, don't even mention it. Or just tell me, okay, I'm not analyzing this because it's statistically insignificant. Okay, this example is very, very, very important, and I would highly advise you to read it carefully. Okay, you have it in 3-4 pages in your textbook, more details. And not only that, you can actually get the data set. You have it on your Sakai site. Get the data set on your Stata and try to replicate this example. Get the same numbers. I did it before and I got the same numbers. So try to replicate at least 1 to 3. You have the data, just run a model, probe it and log it with robust standard error, and try to replicate the numbers. Okay, any question? All right. Next, what I have for you here is one more practice, which is the non-Stata practice, which you have it on your, where is it? You have it on your Sakai site. Let me try to get it here. Okay, wait. Okay, so this is the practice that you have. It's already on Sakai. I'm gonna leave it in Sakai for a couple of days and then I'm going to post for you the answers, okay? So I would advise you to, it's not graded, so just to try to practice it because when it comes to the graded work, which is the exam, quizzes, assignments, you need to have some practice, right? So I would advise you whenever you see anything that is related to a practice, just do it. So what we have here is a relationship that we can see, which is, you can read all the details here between, this is the report of Presidential Commission on the Space Shuttle Challenger accidents in 1986, shows a plot of the calculated joint temperature in Fahrenheit. It's very important to notice what is the unit of measurement we're talking about. The number of O-rings that had some thermal distress. So the data collected for 7 flights for which the thermal distress was identified before the fatal flight and produced this plot. Number of incidents versus temperature. As I can see, doesn't seem to be a linear model, right? It's just some dots are here at the 1, some here, 1 here, 1 here. I don't see any linearity in the model. So as the first question is asking you, do you see any relationship between temperature and the number of O-rings failure? Do you see any linear regression between these 7 observations? Can you like fit a linear line? Like, can I draw a linear line covering these 7 observations? Doesn't seem so, right? So it seems that this is a nonlinear. Of course, it's just a sample size of being really small. It's just a 7 observations, okay? And I'm just discussing it while I'm telling you the answers, okay? And I want you to think about it and answer it fully. So you decide to look at the successful launches before the challenger. What you have is this regression. As you can see, and without me telling you, this is a linear probability model, right? You don't have any phi of z, you don't have any f of z, you don't have any, it's just a linear model, right? And what you need to do is to interpret the equation. Anytime I'm asking you to interpret the equation, move in order: magnitude, statistical significance, sign, magnitude, statistical significance, and then a sentence of interpretation. Okay, so you will really need to move in order when you interpret the results. And as you can see, this is a negative relationship, right? And you don't have to plug it into any distribution function. It's just a linear. So what I can say here, for example, I'm just going to tell you this one. Temperature has a negative impact on the probability of incidence, right? The higher the temperature, the lower the probability of incidence. As the temperature increases by 1 degree Fahrenheit, because this is our unit of measurement, the probability decreases by 3.7%. You have a question about, okay, why is it heteroscedastic? Standard error is used, as I said, in this type of models. You have to use heteroscedastic all the time. So it's kind of the default, okay? Most of the time you have heteroscedastic models with linear probability model. So to be on the safe side, always use heteroscedastic standard error. And then, can you compute for me this model when the temperature is 30? You just plug in here 30, multiply, add, you would get the answer. Okay, and then above which temperature do you predict values of less than 0? So here, actually what you can do is just like math, right? So above which temperature you predict this to be less than 0. So actually you can think of this as being 0 and you solve for temperature. Okay, and I think you will get it something like 77. Okay, so you plug in 0 here and then you solve for temperature to answer this question. Same goes with greater than 1. You plug in 1 here and then solve for temperature, you would get the answer. I want you to, I'm gonna post for you the solutions, but I want you to try to answer it. Now we started a logic regression, and the logic regression is inside a function. So now I cannot analyze this and I cannot analyze this. I only can say that it's negative, and I can compute the statistical significance by dividing these two, getting the t statistic, and you can analyze the statistical significance of temperature. Pseudo R square is telling me there is a 29.7% explanation of the model, right? What's the meaning of the slope? I already said. Calculate the effect of the decrease in temperature from 80 to 70, right? And from 60 to 50. So remember, it's a drop of 10, right? Sorry, here, yes, a drop of 10. So you cannot just take this and you multiply it times 10. You need to have two regressions, as we did with the example of income in owning a house. All what you need to do is you plug in here 80, right? And take the number, have it on top of an exponential function, which is the equation that we have for the logistic function. You get the answer, and then you repeat for 70, right? And get the difference between the two. Next, you do the same for 60 and 50. You get the answers and you take the difference, exactly like what we did. Right, and then why the change in probability is not constant? Because now it's a nonlinear model. Probability, like logistic function is an S-shaped distribution function. So it's no more a constant slope, right? So you need to analyze, like they're giving you two values, like 80 to 70 and 60 to 50, to notice that the slope is not constant. Same here. doing it with a probit model. Okay, so with a probit model, you're going to repeat the same. One time 80, another time 70, get the value from the table as we did with the income example. Repeat 60, 50, and get the difference, right? Again, answer the same question. What's the meaning? Compare the resulting changes. What's the meaning of R square? It's just, or the pseudo R square is about the explanation of the model. Okay. What other measures of fit you want to consider? You can check my video. I have here video on measures of fit. All the measures of fit you can on part 1, binary dependent variable part 1 video. Okay. You can notice that this is 29.7% explanation versus 29.6 is almost the same, right? So when you try to choose which methodology you would use, is it probit or logit based on the pseudo R square, there is no significant difference between the two. You can actually choose whatever you prefer. But if you really want to depend on the number, then you can use the logit because it has a slightly higher explanation. Okay, then next you would calculate the probability of for 80 and 40 using your probit and logit estimates. You would need to sketch. Okay, I know the sketching, I'm not going to ask you to sketch on a Sakai or MyLab. No, probably on MyLab you would have to use a graphic simulator, but in an example like an unstated question, I would not ask you. All right. Okay, and then you decide to run one more regression where the dependent variable is the actual number of incidents. You allow a different functional form by choosing the inverse of temperature and estimate the regression by OLS. What is the predicted? This is easy, right? It's a linear model again. And yeah, so what is your prediction for figure for 31 temperature? You just plug it in and you get the answer. All right. So that's it. So this is an example that is already posted. It is already posted in Sakai PDF file. You can check it out, try to solve it, and I'll be posting for you the solutions. Okay. All right. So I'm done for today in terms of the binary dependent variable. What we need to do for next week. For this week, you need to, of course, study and get ready for the midterm of next week. I want you to, yes, get ready and watch all the videos for week 7, which is the IV regressions. You have actually time to watch it also next week because we're going to cover it on, let me see. So on next Monday, we're not meeting because it's a midterm. So it's on the 19th. I know that I have already scheduled it for the 21st. I'll leave it open from 19th to the 21st. Or then you wanted to have it on the 21st, right? So I will leave it open from the 19th.
Yes.
Okay. Yeah, because it's my mistake. I did this mistake and I typed it as Wednesday the 21st. So what I'm gonna do is I'm gonna open it from the 19th to the 21st night, 11:59 p.m. And then it's up to you. Within the 48 hours to open it, you have the 3 hours window, 1.5 on Sakai, 1.5 on MyLab. And within the 48 hours, you can do, let's say, the MyLab first, and then the next day you do the Sakai. They are totally separate, okay? All right, so on the 19th, which is next week, we're not meeting, but we are meeting on the 26th. And on the 26th, we will, I will assume that you guys have watched the IV regression videos, which are very, very detailed. I think they are very good videos. So I want you to watch and take notes. On 26th, we're gonna do applications, okay? So as we did today, we're just solving questions, theta and non-theta. And I think this is very helpful, assuming that you guys have watched the videos. All right, so I'll see you in 2 weeks then. All right, good luck in your midterm. Just study and let me know if you have any question on the discussion forum. Post any course related questions. Okay, enjoy the rest of your day.
You too.
Thank you.